There I am.
Good evening. Welcome to the Tucson Amateur Astronomy Association July monthly meeting. I'm May Smith. I'm the TAAA president, and I'll be coordinating tonight's meeting. So we have a first speaker with us, who is Jessica Barnes, and some of you got the information on Jessica. Jessica is an assistant professor at the Lunar and Planetary Lab at the U of A, and she's going to talk to us about the latest cutting-edge analysis of the Apollo lunar samples. So Jessica, I think we're getting slides set up for you. Is that right? There we go.
Yep, you should be able to see my screen. Can you see the screen? You can see my cursor moving?
Yes, absolutely.
Excellent. Brilliant. Okay, so let's go ahead and get started. Thank you very much for the introduction and for inviting me to speak today. So I'm going to be talking about Apollo lunar samples and the work that I've been doing. Over the past kind of 10 years, looking at water and lunar samples using new technologies. So I'll just give you a really brief outline so you can kind of keep track of where we are in the talk. So I'm going to overview the types of lunar samples that we have and roughly where they come from on the moon, the kinds of missions that collected them. Then I'll move on to give you a couple of examples of what I mean by next generation sample analysis techniques. Then we'll move on to talking about lunar water and really its discovery and how that's changed the face of lunar science studies over the past 10 years. There are also some unanswered questions that go with those studies, and so we'll talk a little bit about those. And then we'll move on to a really exciting project that's underway at the moment, although slowed down a little bit with current events, but looking at specially curated lunar samples and what those can tell us about the moon and what new insights they might provide. And then I'll go on to touch on a little bit about some planned work and what that might hold for the future. So to start off with, this is a messy slide, forgive me, but this gives you an idea of how many missions have visited the moon and landed on its surface. And in particular, shown with white arrows and the white bracket are sample return missions. So those are missions that visited the lunar surface, collected samples, and then brought them back to Earth. And we have them either at NASA's Johnson Space Center, so those would be NASA's Apollo samples, excuse me. And there were also 3 Soviet lunar missions that landed, and so those samples are mostly curated in Russian laboratories. Not forgetting, of course, that we also have a random sampling of the lunar surface in the form of lunar meteorites that arrive here on Earth after they've been chipped off the lunar surface. So focusing just on the Apollo sample collection, it's a vast collection. Apollo astronauts sampled 6 sites on the lunar surface. And the material brought back totals over 380 kilograms of material. That's a lot of material to work with. And over 2,000 individual samples. The materials brought back range from being rock samples, so here we have a volcanic sample, to being intrusive samples, so magmas that don't reach the surface of a planetary body will kind of arrest in the crust and form a coarse-grained igneous rock. And then we have materials from the lunar crust itself. We also, of course, have lunar soil samples of varying grain size. You can see the famous blueprint here. And we also have some other types of samples. So we have cores that were taken from the surface of the moon. And so they don't just sample what's on the immediate surface, but also give us some vertical impression of what the moon looks like. And so this collection of samples is really unique. We don't have, at the moment, we don't have anything that does better than the Apollo sample collection. It's a very comprehensive suite of samples that are really pristine, and they have exquisite and currently unparalleled geologic context to go with them, because people went to the moon, collected those samples, and brought them back for study on Earth. Oh, and I forgot to mention one sample in the middle, which is a breccia. And so breccias are formed by impact processes, so impactors striking the moon and mixing up all the material that's on the surface, creating a jumble of different types of lunar materials and forming a new lunar rock as a breccia. And so now I just want to focus on a few examples of the ways in which Apollo samples have informed and given us science discoveries, helped us to better understand how the moon formed and it subsequently evolved. And so the first is a very obvious thing. So until we got lunar samples back, we didn't really know what the differences in gray on the lunar surface represent. Now we have a much better understanding. So now we know that the mare, the seas on the moon, are mostly filled with volcanic deposits, volcanic lava flows, and pyroclastic deposits. And we'll talk a bit more about those in a second. And we know that the lighter areas of the moon are mostly high in elevation and also composed of a rock type called anorthosite, which is made up of predominantly one type of mineral, which is a feldspar mineral called anorthite. Now, this early discovery really came about after Apollo 11, looking at the soils that were brought back. And also Apollo 11 clued us into something pretty special about the moon, which is that in order to form a crust on the surface composed of predominantly one rock type, the moon had to go through a magma ocean stage. It had to be either completely or mostly molten at its earliest point in time. And so how we think the moon actually evolved from a mostly molten world to one that's crystalline or rocky, we think it started to cool and magnesium and iron-rich mantle formed. As it cooled, you have progressive crystallization of iron and magnesium-bearing minerals, and then eventually you reach a point where the mineral crystallizing becomes something that's less dense than the magma that surrounds it. And that mineral is the plagioclase anorthite. And so that being less dense than the surrounding liquid would have floated to the surface, creating the crust. And this fundamental way in which the moon cooled has variations on it, but it's been a real sticking hypothesis even from the 70s, and we still use it today. Another important scientific discovery that was made from Apollo samples is that from Apollo breccias, we can really understand the impact history of the moon, not just in terms of understanding how different materials are brought together and mixed to form a new rock type, but also what materials were bombarding the Earth-Moon system throughout its history, because we find meteorites in Apollo samples. So this is the bench crater meteorite. It's a piece of a carbonaceous chondrite meteorite, but it was found inside an Apollo 16 regolith breccia. And so from the moon and lunar samples, we have insights into not only what was striking the moon during its history, during over 4.5 billion years, but also what was striking the Earth. And that's important because we don't have that geological record that extends all the way back to the beginning of Earth's history left on the Earth because of the action of plate tectonics. And so this is just a little glimpse of the science discoveries that have been made using samples. But what I really want to talk to you today is about some new work that's been done using new techniques on those samples. So those discoveries that I mentioned to you have been happening over the past 50 years, but it's only been in the last 10 years that we've really been investigating lunar water, which I'll talk to you in a second about. So first of all, what do I mean by a change in the state of the art of analytical techniques that we use in the laboratory? Well, there's been a change in the way we visualize samples, and hopefully this video plays. Now we can see in super high resolution lunar samples in 3D. So hopefully you're seeing a video. May, can you give me a little nod if you're seeing the video playing? Someone give me a thumbs up, thank you. So what you're seeing here is a 3D visualization of a whole rock sample from Apollo 11. The differences in color represent differences in density of the minerals that are present within that rock. And so lighter minerals are more dense minerals and darker minerals are lower density. So we can see, I'll play that for you again. So we can see in depth what these rocks look like in the center. And so that helps us to make better informed sample preparation decisions. If we want to, for example, go in and take a piece of a sample, we know better where to cut that sample up. Other changes or advancements in state of the art are getting down to super high spatial resolution. So being able to see things that just weren't possible in the Apollo era. Here you're looking at a high resolution transmission electron microscope image of a lunar soil grain. And you can see particles of iron that are in the 200 nanometer range. That's incredibly small. That's a fraction of the width of a human hair. And so from that, we're able to understand space weathering processes happening on the moon. And something what we're going to talk a lot about are now we're able to make in situ stable isotope measurements of water in lunar samples, which just wasn't possible in the Apollo era. So not only can we make those isotope measurements, but we can, with high precision, place those measurements exactly where we want them on our sample to gain the best information possible. And so these are just a few examples. There are many more advancements that have been made that allow us to get new insights into samples that have been on Earth for 50 years. So these improved analytical instruments, also methods and new ways of preparing samples really does give us a new outlook on the moon at a much higher resolution than we've ever been able to in the past. Okay, so now I want to move on to lunar water. So for about 40 years, the moon was considered to be completely bone dry. Astronauts didn't see running water on the surface, of course. There were no remote sensing observations that indicated there channels carved by liquid water on the surface. And Apollo samples that were brought back, while they were analyzed for water and people tried to find it, there was no way to untangle the results that people were measuring from terrestrial contamination. There was no way to say for certain that what was being measured in the 1970s was actually lunar water or whether it was just terrestrial contamination. And so until the early 2000s and late 1990s, this wasn't really revisited. It kind of was left, that was a known fact. The moon doesn't have any water. That's until the late 1990s and early 2000s when several orbital missions that did remote sensing observations of the lunar surface detected water, hydrogen, and hydroxyl all over the lunar surface. And so that's what you're seeing here. This is a moon mineralogy mapper, some M-cubed moon mineralogy mapper. It was an instrument on board the Chandrayaan-1 spacecraft, and it orbited the moon and detected signs of hydroxyl, OH, all over the lunar surface. So you see here that the moon is pretty much all of it's colored. Blues and purples represent high quantities of hydroxyl, and reds are lower quantities. But you can see that there are at least detections all across the lunar surface. Yes, concentrations at the poles. These data sets really confirmed that yes, water was present on the lunar surface. We didn't know that before. That water really varies in its abundance, both laterally and with longitude, and highlighted that potentially the moon's a really important place to go to use water as a resource for future exploration. But the question, it posed another question, which is if we can find water on the surface and the exterior of the moon, can we find water in the interior of the moon, i.e. in lunar samples? And so, armed with this new data and new state-of-the-art laboratory equipment and the, can we say, old Apollo samples, a group from Brown University and the Carnegie Institute in Washington used the famous orange Apollo volcanic glass beads and their new nanoscale secondary ion mass spectrometer to detect for the first time water in lunar samples. And this just was not possible in the Apollo era. You needed this combination of the drive due to the detection of water at the surface, the new state-of-the-art analytical equipment, and the right samples in order to detect this water. And this paper that came out in 2008 was really the driving force behind a brand new area of lunar science, targeting understanding the volatile history of lunar rocks and where did those volatiles come from? because until that point, it wasn't an active area of research. So before going on to the main findings of lunar water, I just want to step back a second and see, well, how do we actually water in the laboratory? What do I mean by that? And so many of you probably aren't familiar, but most of the work that a lot of people who do in situ science do are they look at thin sections of rocks. So these are just what they say on the tin. They're thin, approximately 30 micron thick slices of rock samples that are basically stuck to a glass slide using epoxy and polished very, very flat until they get a mirror shine to them. And you'll see here a comparison with the width of a human hair. When I say thick, I actually mean thin slice of a sample. And then when we're measuring lunar water in the lab, we're basically doing an isotope analysis. And what this means is we're targeting a primary ion beam, so a beam of ions at a sample, and we're basically eroding the sample surface. And during that process, both negative, positive, and neutral ions and particles are released from the surface. And in this case, we're only going to be measuring the negative ions that come off that surface. We're going to transmit them into a mass spectrometer and measure the isotopes of, in our case, when we're talking about water, we're going to focus on hydrogen, deuterium, or hydrogen-2, and also maybe we would look at oxygen-18. And we would measure those in detectors. What this looks like after you've done the analysis is you end up with little tiny holes in the sample surface. And also, once you've done standardization and you've corrected your data, you end up with a water content for a given spot, and also a deuterium to hydrogen ratio. And this is really the moneymaker right here. The deuterium to hydrogen ratio, we can use that as a fingerprint because different objects in our solar system have different deuterium to hydrogen ratios or hydrogen isotopic compositions. And this allows us to basically trace water throughout our solar system to understand the kinds of objects that were impacting, in our case, the moon. So I'm going to walk you through basically the two broad sample sets that we have. And the work that I'm going to show you is a compilation of, as I said, about 10 years of work and numerous different authors from different groups across the world. So the story that we've been getting from volcanic samples, that means either basalts or you can think of them as lava, crystallized lava flows, and also these glass beads, are that those samples contain variable amounts of water in their minerals or their glasses. We've also seen that they contain very variable hydrogen isotope compositions, ranging from approximately Earth-like to over 2 times Earth, which doesn't sound like a lot, but it's outside the realms of anything we have here on Earth. It's completely what we would call fractionated. It's very rich in deuterium. And in some cases, we see correlations between the water contents and their hydrogen isotopic compositions. Now, when we think about how these volcanic samples form, we know that they erupt onto the surface as lava flows, or in the case of the glass beads, they erupt in these fire fountain conditions. Of course, this is not the moon, this is Hawaii. But to illustrate the point, these pyroclastic deposits, they erupt molten pieces of the magma into the essentially vacuum of the moon, and they crystallize into these little glass beads. During this process of eruption, we think that in order to create these really high deuterium to hydrogen ratios, there must have been some loss of the volatiles dissolved in those magmas, those melts, must have been lost as a gas as the pressure was released as these erupted. And this loss means a permanent change in the character or the composition of the water that's left behind. So if you're losing hydrogen to space, you're going to change the deuterium to hydrogen ratio of what's left and what's recorded in that rock once it cools. So we can directly tie volcanic and magmatic processes that happened in lunar samples to the variability in their water contents and their hydrogen isotope compositions. The second suite of samples are what we call plutonic samples or intrusive samples. And so these are the ones that, for the most part, are much, much older than the volcanic samples that I just showed you. They're more than 4 billion years old. And they didn't make it to the surface, right? They are magmas that arrested in the crust very early on, and they cooled slowly, meaning that they have coarser grains. So here you can see olivines and feldspars with the naked eye without needing to go in and use a microscope. The results that we've obtained from those samples indicate that they too contain variable amounts of water in their minerals, but they seem to have a consistent deuterium to hydrogen ratio across different sample suites, anywhere from just below Earth-like to Earth-like. And as I say, these rocks formed a long time ago and as magmas that stalled in the crust and then cooled slowly. And so we think that these samples are actually recording their magmatic signatures due to a limited loss of volatiles as they've been slowly cooling. And so whereas the volcanic samples are telling us about volcanic processes happening on the moon, these samples are potentially recording their original magmatic composition, or the composition of the melt that they would have originated from in the lunar mantle. So far, yes, we've detected water in lunar samples, and that's all thanks to technological innovation and advancements. It just wasn't possible in the Apollo era to detect these, to A, make the measurement, or B, differentiate that measurement from terrestrial contamination. A result can be terrestrial-like, but if you can account for terrestrial contamination, then what you can just say is that the deuterium to hydrogen ratio of a lunar sample is similar to Earth, but it's not terrestrial contamination. We've also seen that the water content across many samples is variable, suggesting that there's a heterogeneous distribution of water inside the moon. So the magmas that were rising throughout the crust and then maybe onto the surface, they contain variable amounts of water having come from different places inside the moon. We've also seen that the deuterium to hydrogen ratio of lunar water is highly variable, with some being attributable to volcanic processes like volatile loss or degassing, and also to crystallization processes. And also in some cases, secondary processes that happened on the moon. Oh, okay. In the other instance, for the plutonic samples, we saw that some of those seem to have experienced limited water loss or limited separation of hydrogen isotopes. So their hydrogen isotope signature seems to be resembling the composition of the magma from which that rock formed. More interestingly, it seems that that composition is very similar to what we consider for Earth, which is actually a very narrow range that we find on Earth, and also very similar to the composition of some types of carbonaceous chondrite meteorites, which seems to hint that there's a link between the heritage of water in the Earth-Moon system and maybe something, maybe some contribution from chondritic meteorites. And so that's just illustrated here in that if there's a similarity in water in the mantle of the moon and also that of the Earth, then maybe water was just inherited during the moon forming impact event, because the moon largely formed from Earth's mantle material. Or Earth-Moon system had formed, but while it was still in a kind of semi-molten state, the accreting moon accreted volatiles, including water impactors like carbonaceous chondrite asteroids. So that's kind of the picture at the moment, but there are still quite a few unanswered questions. So we still expect origin of lunar water, as I just mentioned, is kind of up in the air at the moment. And there could be multiple sources, even multiple sources from different types of chondritic meteorite. We still don't know the extent to which volatiles are heterogeneously distributed within the moon, and this can be addressed by looking at a more diverse set of lunar samples, and also by getting samples back from the lunar poles. We also still have some questions about the thermodynamic evolution of the Earth, or sorry, of the Moon, and how water might affect, for example, moon formation models. And we still don't know the relationship between interior or magmatic water, the water we're measuring in lunar rock samples like the basalts and the plutonic samples, and what we're finding on the surface of the moon. And so much more work is needed to kind of address these open questions, but that's kind of where the field is at the moment. Now, going on from here, what we hope is that a new set of lunar samples that just became available might help us to address some of these questions. And so in 2019, NASA announced the selection of 9 teams to study newly released or new Apollo samples. And by new, these are samples that have been unstudied since they were returned from the moon. So they've been sat in the cabinet at JSC, not NASA's Johnson Space Center, for about 50 years. And they've essentially been untouched. And NASA released a new program called Apollo Next Generation Sample Analysis, or ANGSA, as a program to maximize the science derived from samples returned by the Apollo program using new techniques. And these are anticipated to inform space missions going forward, so Artemis and beyond. The unstudied samples include unopened core samples, and unopened core and vacuum sealed core samples, samples that have been stored frozen, and also samples that have been stored in helium. And so today I'm just going to quickly, in the last few minutes, whiz through 2 of those investigations, and they're the ones that I just happen to be involved in. And so we at the University of Arizona are leading a team of 7 US-based researchers to look at volatiles, including water, in 4 Apollo 17 basalts. 3, like this one here, 71035, have been available for study since they were brought back in 1972. But 71036 that you see down here, after it was photographed, was put in cold storage and has been there ever since, untouched and unstudied. The other investigation I want to talk very briefly about is the ANGSA core consortium and preliminary examination activities. And these are 2 sets of cores, that we'll go to in a second, that are being investigated by a team of over 50 researchers from across the world. So, to move on, first of all, to the U of A study. So we're looking at 4 samples that were collected from the rim of Steno crater. You can just see a coarse outline here in yellow. And all these samples were chipped from this boulder. And you can see, I think this is Jack Schmidt in the photograph here. And you see the sample numbers here. This one in the middle, 71036, is the one that has been frozen for 50 years. And so our study is really to do an very in-depth laboratory investigation of these 4 samples to compare the frozen sample to the ambient samples. And this is going to be the first time that such an in-depth coordinated study has been done for both the morphology of the samples, their mineralogy and their petrology. So how did these samples, how were they formed and how did they crystallize and what's happened to them since then? Looking at their geochemistry, including their water contents and their deuterium to hydrogen ratios, and then trying to determine their eruption crystallization ages and also their surface ages. So at what point in time were these samples exposed at the lunar surface? And through that study, we're hoping to address whether the water content and signature is different or the same between the ambient and the frozen samples. That's going to tell us something about curation practices. For example, do we need to keep samples returned by Artemis frozen or not? We're going to see whether these samples in particular record a history of volcanic degassing, whether we can see preserved in the rock record that volatile loss. We'll see whether we can see a signature and maybe the origin, whether we can determine the origin of lunar magmatic water at the Apollo 17 site, which is very understudied. And we're going to be able to tell whether these basalts are similar geochemically and whether they represent the same lava flow or not. We received the first batch of samples for this study in February, and we got a little bit of data before our fun time in the lab was cut short. But here you can just see some preliminary work from LPL grad student Zoe Wilbur, where she's been using an electron microprobe to look at the elemental abundances and the distribution of different minerals within one of the unfrozen samples, the ambient samples. And hopefully next spring we'll be getting the frozen sample, but it requires in the meantime that NASA's Johnson Space Center can make a dedicated cold sample processing cabinet to keep that sample frozen at -20°C during processing. So I ask you to stay tuned, and hopefully I'll be able to give you a better update in a year or so about those samples. And finally, moving on to the core consortium, this is a core sample that was taken at Apollo 17 Station 3. You can see one of the astronauts actually taking the sample, and that's the core in the ground, so to speak. And this is the location here. And this core is composed, it's a double drive tube, which means it is made up of two different sections. So we have a top part, so this is the surface schematic. The top 22 centimeters are present in 73001 sample number, and then the bottom half is 73001. This top sample was not vacuum sealed on the moon, and it remained unopened until last fall. 73001 was lifted out and immediately put into a vacuum sealed container and sealed shut, and has not been opened since it was sealed on the moon. Now, I'm going to leave you with the opening of 73002, the unsealed, unvacuum sealed core sample. It was opened last fall, and this is another micro XCT, micro X-ray computed tomography scan of the whole core of the top half. And you can see just the wealth of information in this video here. This is a comparison between what was possible last year and what was possible, I think, in the 1970s or 1980s. So we can get a huge amount of detail from these scans. I'll just play that again, compared to what was possible previously. And actually, I think this image is made up of over 6,000 slices or 6,000 images that can all be dissected, and you can go in and look at each slice and look at each little class individually. Oh, how do I move to the next slide? Okay, so I just want to wrap up by saying that Apollo samples really are priceless. They're the gift that keeps on giving, as a colleague of mine likes to say. We still have many unstudied lunar samples, so samples that maybe were studied very early on in the 1970s, but they just haven't been revisited. And so there's a lot of wealth of information that's still out there to be gained. Hopefully I've proved to you that the application of new analytical techniques really does yield new information, sometimes even revolutionary insights into the moon as we know it. And the ANGSA project, which is ongoing and has been stalled for obvious reasons, is going to be really crucial for maximizing the science return from an unopened sample, as we all have to work together to get the most out of these samples. And it will be really informative for future sample return missions from the moon. And it's essential for training the next generation of lunar scientists. And here you see myself and my graduate student Zoe at NASA's Johnson Space Center helping to dissect that recently opened core sample. This was taken in October. So that's it, and thank you very much. I was a little bit over, apologies for that. May, I think you're talking, but your mic's off.
Yes, very true. Thank you. Thanks so much, Jessica. I'm going to wait a minute here for people who have questions to get their questions entered in the chat if they haven't done that. And in the interim, I'll just go over what the schedule is going to be for the rest of the meeting. We do have a second speaker who's going to be talking with us, and we'll take questions for her, you know, in the same way that we're taking them for Jessica. And then after that, we will say goodbye and thank you for coming to our Facebook participants. And then we'll have a couple of other things that we want to do with members, one of which has to do with the election. And it's really important that people attend that if possible. So we hope that people can stay for that. So now, Jessica, in chat, I have a question that says, when were the lunar samples frozen? How soon following their collection on the moon were they frozen?
Oh, that's a great question. So let me just zoom back real quick. Hopefully you can still see my screen. Yes. Okay. So this sample, it wasn't frozen on the moon, so they didn't take like a little refrigerator with them. The astronauts, when they were brought back to Johnson Space Center, it was within about, we think, the records are a little bit rusty, but it was within about 2 weeks of being on Earth that sample and several of the other samples that were frozen were put into cold storage. So a couple of weeks. But they've been that way for 50 years, and actually they're still frozen because, as I said, the cold processing cabinet hasn't been fully developed yet.
Thank you. Okay, Jim, do you have some questions from Facebook?
Negative. We did not have any questions from Facebook. We had several that gave some thumbs up and thought it was a very good presentation.
Great. Well,
Awesome.
It's nice to have some comments then. Thank you. Okay. Now let's see. I have a question here from Doug, who says, "Can the speaker give us a hint of any large volume water sources on the moon, such as in dark craters?"
Ooh, that's a good question. So as I mentioned at the beginning, we really don't know how much water is up there. And that's due to a mixture of things, differences in the kinds of technique actually analyze for water remotely. They're the kind of the spatial resolution to which they can measure. And so it's likely that permanently shadow craters, I think this is what Doug is alluding to, permanently shadow craters are the best target to go to look for large volumes, tons of amounts of water. But we really don't know exactly how much is up there, which is part of the driving force behind the Artemis program and behind, you know, not just NASA's desire to go back to the moon and go to the poles, but also, for example, the Chinese mission, which is currently up there, Chang'e 4. The European Space Agency is also planning to go back with Russian colleagues to the lunar surface to look for, we need robots or people on the ground to tell us how much is there, to actually measure it in situ, and to bring back samples so we can assess how much is actually there and try and extrapolate that across the globe to really ground truth what we're seeing from orbit. But potentially the global inventory could be in the millions to billions of tons of water, potentially.
Oh, wow. Thank you so much. Okay, Marshall has a question. With all of the findings, does this mean possible new missions to the moon?
Oh, definitely. So every time we make a new discovery, we're pushing that new discovery to test ourselves. We need to go to other places on the lunar surface to test the results and the big hypotheses that we're coming out with. Lunar meteorites give us a global sampling of the moon, but we don't know where they came from exactly. And so what we need are new space missions to go, for example, to the far side of the moon and to collect samples, and also to go to the polar regions, as we've just talked about. So when we write, you know, white papers to NASA, we include all of these new findings because they really are the driving science behind new missions, as I think it was Marshall just asked.
Super. Okay, Ed has a question. how is the pandemic affecting the plans for the sample study?
That's a great question. So currently there's no work ongoing at NASA's Johnson Space Center. So all dissection of the core has stopped. They managed what I didn't show you, hopefully, maybe I have another slide. The core, I think I do have one more slide. Yes, so the core is currently, you can think of it being horizontal, and these plates that you can see here allow us to go down into the core kind of crossways. And so what the first pass was done, so we went all the way from where you see this 18 centimeter mark all the way to the back end of the core. And then they were just ready to take off the plates and kind of go down, I think it's a centimeter in depth, when everything was shut down. So hopefully when things start back up again, we'll be able to start dissecting through the core again and pulling out nice clasts like this one. And yeah, as far as our laboratory analysis, luckily we're just starting to ramp back up, maybe. But everyone's on hold at the moment. So we just have to wait patiently until we can get back into the lab and it's safe.
Terry has a follow-up question. When the samples were water sealed, were they vacuum sealed during the 2-week delay that you had? I think there was a 2-week delay between when they were collected and when they were frozen.
Oh, I think this is referring to the frozen samples again. So this sample was collected on the lunar surface. It was chipped off one of the boulder that I showed you before. And it was just brought back like any other rock. And then it was put into cold storage after 2 weeks. The vacuum sealing is different. So that's a vacuum sealed sample. So it was pulled out and vacuum sealed on the surface and has remained that way ever since. This core has not been kept frozen. So there are different types of unstudied lunar materials. There's unopened samples like the cores. This one is vacuum sealed, and then there are frozen rocks and soil samples, and also some stored in helium gas.
Okay. So lots of variety there to work with.
Yep.
Okay, Vern has a question. Are human missions necessary to collect these samples, or can robots do it?
That's a very interesting question. So technically, no, humans are not necessary. 2 examples I can think of are the Luna missions. They were uncrewed missions, so no people involved. And then also Perseverance, or Mars 2020, which is going to go to the surface of Mars, is a robotic mission planned to cache samples on the surface, samples of geological interest, leave them there, and then later in the future, another robotic mission would collect those samples. So no, humans are not necessary, but when you compare, number one, the amount of samples that have been brought back by crewed missions, it's substantially more, so you get more bang for your buck, even though crewed missions are much more expensive. But the most important thing is that all the astronauts who were sent to the moon were trained in geology, and there's a saying that each astronaut who went to the moon and collected sample, or each astronaut in the Apollo program, basically had a master's degree in geology by the end of their training, because they were trained on which samples to look out for and what different rock types meant, so that they could on the fly pick up samples that they knew were going to be of interest to the scientific community and really inform us about geology and about how the moon formed and evolved. If they didn't have that training and they weren't people doing the picking, maybe we would have ended up with 380 kilograms of soil. And that would have been interesting, but we wouldn't have had the large variety of rock types that we have, which have been instrumental in informing us how the moon formed and evolved.
And my understanding is that some of that training for those astronauts was done at the Grand Canyon. Is that right?
Grand Canyon, I think Meteor Crater, and there's another place in Arizona that I'm forgetting where it was. But yes, they've done a lot of training in Arizona. for obvious reasons, right? Desert
Yes.
landscape is a good place to train. It's a good lunar analog in the United States.
Super. Thank you. Okay, Jim, I don't have any other questions. Do you have any on your list?
Nope, there's none from Facebook, so we're good here.
Okay. Well, thank you so much, Jessica. This has obviously been really interesting, and people, you know, got involved and had some interesting questions for you too. So thank you
For
so
sure.
much. We appreciate this a lot.
Thank you very much. I appreciate the invitation.